Hello there.
Hi, everyone.
Thanks, Daria. Thanks, Ryan.
Are you going to share the presentation, Rhett?
Yep.
Yep, good.
Let me just pop it up. Okay. Thanks for the opportunity to present this piece of work that was done between my company, GHD, and Jared's company, New South Wales Ports. Just before we begin, I'd like to acknowledge the Aboriginal and Torres Strait Islander peoples as the traditional custodians of the land, water and sky throughout Australia on which we do business. We recognise their strength, diversity, resilience and deep connections to country. We pay our respects to elders of the past, present and future as they hold the memories, knowledge and spirit of Australia. We're committed to learning from Aboriginal and Torres Strait Islander peoples in the work that we do. So to start this off, I might pass over to Jared to give a bit of background into Port Botany, and he can do it far more justice than I could. Thanks, Jared.
Thanks, Rhett. I can't see the presentation on this screen, but I do have it open on another screen, so I'll just go off that. So just a bit of a brief introduction to Port Botany and the problem that we were trying to solve with this model. So Port Botany is the second largest container port. It's located in Sydney, Australia. We handle around 2.8 million TEUs per year. A TEU is a 20-foot equivalent unit, so that's about 1.7 million individual shipping containers in and out of the port each year. Over 40% of all the household goods that are consumed in New South Wales actually come through Port Botany in a container. The port contributes around $13 billion to the New South Wales gross state product, so it's a significant asset and contributor to the state economy. Support around 52,000 direct and indirect jobs. That's at the port and in the supporting supply chains that go along with it. And the problem that we were trying to solve or seeking to solve with the model, which Rhett will explain, was around how do we grow our rail mode share. So there's two predominant modes of transport for shipping containers once they come off a vessel, and that's road or rail. Our rail mode share is critical to optimising the total capacity of the port and to reducing what is a major problem around Sydney, which is road congestion.
I'll jump to the next one.
Okay, thanks, Rhett. So as I mentioned, targeting the increase in our rail mode share was the purpose of developing the model. So our rail mode share currently sits at around 15%, and we do have a plan to try and increase that to 40% by 2045. To put that into context, it's going from around 400,000 TEUs per year to around 2.5 million in that period. So it's a significant increase in anticipated throughput on the rail. What we have at the moment is some challenges, particularly around rail scheduling and inefficient rail operating models and some constraints with infrastructure. So we were developing this model so that we could test some different scenarios and change some of those parameters to see what impact that had on the volume of containers that we could transport by rail. Next slide, Rhett.
Yep.
So I think this is back to yourself now.
Thanks. Yeah. So I guess why was simulation needed to help answer these questions around rail capacity? And it's because port supply chains are complicated beasts. So they're a tightly integrated supply chain that consists of many different components. And I've kind of sketched it out at the bottom of the screen here. So ships come in, they drop off cargo at several different handlers, which are called stevedores at the port. That cargo goes via rail or trucks inland, and it doesn't end there. There's a whole inland infrastructure as well set up around the handling of cargo, so getting it from the rail yards to customers, and then of course getting all those containers back out as exports on ships the other way. as you might have guessed, there's from the collection of stevedores there's many different stakeholders along the supply chain that includes cargo handling. There's the people who own the cargo containers themselves, and there's 20 of them. They're called shipping lines. And there's various state government bodies that handle various aspects of the infrastructure, such as rail. So there's a lot of people to have to be convinced of any solution. And there's many different ways to influence the rail throughput of a port supply chain that involve either changes to scheduling, operations, or infrastructure. And tweaking those levers has impacts that sort of flow on to the rest of the system. So they're highly interconnected. Where GHD was brought on board, we were brought on board to take the existing model that New South Wales Ports had that mainly looked at container flows, and it sort of expanded, especially around the rail area, to assess those infrastructure and operational changes. And I've taken and put a blue box around the area that was increased in the detail of modelling. So prior to this, it was existed effectively as a container flow model. The containers were modelled as individual agents with owners, and a lot of process block flows. But we had to include a number of different components to realistically represent the rail side of the operation. So one of those, as an example, is the simulation that had to play out alternative train schedule and rebooking rules. So I've got a visual example of that here. There's a rail schedule with the input at the top, and it shows for a week different rail slots. Different trains are assigned to come in at different times. And then on the bottom, there's the output from a given week of a simulation that showed how what trains actually came in. And there's a number of different things that can happen. So there can be free slots that can be given to a particular train service. There can be rebooking of a train slot if the existing train is not going to meet certain utilisation targets. And there can also be things like cancellations. So we had to build some bespoke scheduling classes that allowed the searching, removal, and modification of a schedule dynamically, as well as being able to opportunistically slot in trains in blank spots if needed. The other thing the simulation had to do is play out train shunting and cargo loading processes. So here's an example that I've got that shows the limitations on the trains that can enter and leave port. So there's a sort of black and white schematic here with a number of different trains at different stevedores at the port that are ready to depart, but they can't leave until a train that's currently shunting in has pulled in all the way, and only then can one of the trains leave. So the model had to be flexible enough to be able to explore these different kind of infrastructure modifications. And so it needed expansion with a number of different dynamic event scheduling techniques. This is how we used how the rail capacity limits were tested with the model. And I've sort of shown it visually over here on the right, and I'll talk through it. There's a red line with some dots, and each dot is the outcome of setting up a scenario and running it for a year. So what we would do is set up a scenario with a given infrastructure, a different set of options, and then run it and check what the rail cargo throughput was. Then what we would do is construct a number of different scenarios where we would scale up the total amount of cargo that was coming in at the boundaries of the system. And if everything's working fine, then rail cargo grows linearly as we add cargo until it reaches it starts hitting certain capacity limits. And then the rail cargo throughput stops growing as we continue to scale up the cargo entering the system. This isn't the only marker that the system is hitting capacity limits. We also see other indicators such as cargo dwell times and imports and exports building up. So using this approach, a staged infrastructure upgrade pathway was identified. So again, we've set up different scenarios with different types of rules around infrastructure and operations, and they're in different colors here, and then push them to their limits to see where they fell over and find out what the rail capacity was going to be. So starting off at a current day rail usage throughput, built the base case in red, pushed it to find out what the future rail capacity would be if business as usual continues. Then on top of that, there was roughly in the blue here, 20% plus 20% potential gains that we could get by altering the rail scheduling alone. And then further on top of that, there was in this yellow line, yellow dots here, there was a roughly 120% additional rail capacity, which is about 10 years worth of rail capacity that could be unlocked from a critical bottleneck, infrastructure bottleneck in the system. So I'll just come back to this, and I've got the image playing out on the right, which is the animation of the simulation, and you can see the ships coming in and depositing cargo, and trains and trucks running around and taking cargo off to the hinterland. So yeah, we were able to identify a number of both operational changes and critical infrastructure changes to unlock certain milestones and sort of prove it up that they would be effective. And the other important thing was this was built on top of a model that already existed, and it was important to have it in a state that the model could then be continued to grow in the future as additional business questions arose. So I might pass back to you, Jared, just to talk about what New South Wales Ports is currently using the model for.
Yeah, thanks, Rhett. So the model that Rhett and his team developed for us has been absolutely fundamental in us being able to develop a rail strategy for Port Botany. So we've used this model to, as Rhett outlined, test a number of different scenarios and understand what some of the benefits to our business will be through operational changes or investment in infrastructure. There's a little graph there at the top right, or a little image showing a train operation. That is an operation that was born out of this rail model and testing different scenarios. And this was an operating model that we believe is the most efficient model for the port, and that's based on the outputs of the modeling that were done. We're also using the outputs of the model to advocate for change with federal and state government here in Australia around supporting the increased use of rail, particularly around rail access on the Metropolitan Rail Network in Sydney, which is a shared network between passenger trains and freight trains. And being able to present actual outputs from the model has been very beneficial in that advocating process. We're also using the model to assess some of the environmental benefits of rail. I'm sure everyone is aware of sustainability and environmental benefits being at the forefront of most businesses, particularly in supply chains, which are very heavy industries and do cause a lot of emissions. So being able to use the model to generate different scenarios and test what the output in terms of the environmental output of different scenarios has been beneficial for us. And we're also using the outputs from the model to support business cases for investment in infrastructure. As Rhett mentioned, there was a significant bottleneck that was identified around the shunting of trains, which in layman's terms is moving trains, moving them around each other. And we've been able to identify that in the model, and now we're using the model outputs to develop a business case to present to our owners and our board for some funding to develop new infrastructure to remove that bottleneck. We're also using the model to support business cases for investment in other rail infrastructure. And what you can see there with the image at the bottom is a automatic rail unloading crane. So you can see that crane's lifting a container off a train. That's all automated. There's no human intervention at all in that process. That's technology that we've invested in now and will continue to invest in across the port, and we're using the outputs of the model to support those business cases.
Great. Yeah. So thanks everyone for listening. I'll take questions in a moment. I just would like to also acknowledge the wider team that was involved in the work as well, because it takes a bit to build a model like this. I've only got one screen, so I'll just have to stop the share and have a look at the questions. All right, cool. So we've got a question from Sakar. How does the model decide whether a rescheduling is needed? Is there an optimization algorithm involved here? Yeah, so the way it works in regular mode is it makes decisions based on the expected utilization of a train. So the train will look at some time in advance of when it's meant to be coming in to the port, and it will look at the amount of cargo that's going to be expected to be loaded onto the train. And then based on whether it can meet certain utilization targets, it will make a decision about whether to cancel the train or send it in. There's similar algorithms involved around making that the decision for whether a different train should be sent in. It's pretty much all based around how much cargo is there, and a few other rule constraints around not having too many trains come in at once. Urshad asked what parameters of sustainability environment is considered in the model, and how. So,
do you want me to answer that one, Rhett?
Yeah, go for it, Jared.
Yeah, so what we've done is we've attributed fuel usage to the locomotives that are obviously hauling the trains. So we'll run a scenario in the model, understand how many trains came to the port through the model run, and how long the duration that they were in the port environment. And from that, we can calculate what's the fuel usage from those locomotives, and then we can understand from the amount of fuel that was burnt, what is the emissions that was that were generated from those movements. We can then look at that against the amount of cargo that was handled and calculate a number based on the number of containers that were handled. So that essentially the emissions factor per container. We can then run that over multiple different scenarios with different operating models and different infrastructure parameters to see how that affects that number and see what is the most beneficial model.
Cool. Let's see, the next question is from Victoria. Do you find which correlation train schedule and infrastructure have and incorporate that in the model behavior? Okay, so the way we went about deciding what to include in the model is we sort of worked hand in hand with Jared and his team to just talk through and know what the key process is, both around trains coming in, what they needed to do to come into the yard, load up, unload, get out, and the various key constraints. So and we built all of those into the model. And then in order to understand which is the sort of key driver of rail capacity, we ran a lot of sensitivities pretty much. I think many hundreds of simulations ultimately. Lewis asked, is AI reinforcement learning integrated in the model? No, there's no AI or reinforcement learning. Someone else asked, how long was the project to develop the solution? What were the key hurdles in developing the model? I can have a go at this again. So yeah, It was several months of effort, ultimately to both build up the rail component, and then to actually run the study. I think, like anything, the key hurdles was just making sure that some of the operational rules were sort of well enough understood in order to code up. Also, the other tricky thing I think is being able to generate schedules to test out that don't exist yet. So that was a bit of work went into that as well.
Yeah, and I think just further to that, Rhett, as you mentioned, this model was development on an existing model that had already been built, which took around sort of 6 to 8 months to build the original model. There was a number of learnings that came out of that original model build. As you also mentioned, ports and supply chains are incredibly complex, and there is a number of different sort of parameters that could be changed. And what we found from the first model that we developed was that we probably tried to be too detailed and too complex in that model, and it overcomplicated things. And we as a business and NSW Ports, who engaged GHD to develop the model, probably went further than we actually needed to in that stage to answer the questions that we were trying to answer. So that was definitely a key learning from the first model build to this model build with the rail, was to try and simplify it and focus on what are the key parameters and what are the key questions we're trying to answer.
All right, we have there's another question from Evelyn. How to make a cost-benefit analysis in real case. So, yeah, I think that's how is the cost-benefit or business case sort of built up. Jared, I might pass to you for that one.
Yeah, no problems, Rhett. So we've used the model to demonstrate the value that rail can bring to our business. So rail, it brings a lot of intangible benefits, such as reducing road congestion, such as reduced emissions on a per container basis. There's a number of other amenity issues that are solved with the use of rail, noise issues, and that sort of thing. So we've been able to use the model to feed some of those outputs into an overall business case to try and quantify the dollar value of what those things are, which we can then show that the investment is delivering on what are somewhat intangible benefits with a dollar value then attached to them.
Let's see, John asked, how did you model the difference between human-operated movement versus robotics-operated movement? So I can have a go at this one. So the abstraction level was around the actual cargo movement and handling in yards was quite high. So there was not a detailed modeling of movement of cargo within those yards. Mostly for that particular component of the model, it was done at a higher level around process times and sampling from a process time of moving cargo around. So yeah, it wasn't a detailed cargo movement model within the yard itself, though. Let's see what else. Have another question, anonymous. What did you discover during the simulation development that was counterintuitive for the stakeholders, making it difficult to push the simulation forwards?
Yeah, I can answer that.
Okay.
I don't think we actually discovered anything that made it difficult to push the process forward and develop the simulation. We had a pretty clear understanding of what the questions were that we were trying to answer. And as I mentioned, we kept the model at a level this time which we felt was sufficient to answer those questions without overcomplicating it. So from the experience of developing the initial model, we had a much better understanding of what was required, what sort of data we needed to be able to feed into the model to get a representative output that was useful to answer those questions.
It's a question from Shingen. Do you think about reship of cargo from ship to train? So within the model, there's cargo, there are imports that come in on ships and they can leave to go inland via road or rail. There was also transshipping where cargo stayed at the port and then was taken out on other ships. And the other side of the equation there was the cargo exports. So exports come from the hinterland inland and then moved to port and went out on ships. So those were the kinds of cargo movements that were considered. All right, Jonathan asks, did you use ABS or discrete event simulation? So the answer is both, because both agents are used in the modeling, and it's a discrete event based system with discrete events. So yeah, the answer is both. Karen asks, to what extent was container storage modeled in terms of storage, retrieval, and rehandling?
So I can answer that one if you want, Rhett.
Yes, thanks, Jared.
So the model, as has been mentioned, actually starts with the containers coming in from the vessels calling into the port, and then there's a schedule, a rail schedule that's developed and then dynamically developed over time. So those containers are discharged from the vessels based on the vessel arrival and departure schedules. Then the storage is the period between when they've arrived and when they depart, either on the train or the truck. And then similar coming back the other way, the trains will be operating to their schedule, dropping off cargo, and then the vessels are operating to a schedule as well to collect that cargo for export. So we've sort of covered the entire movement of the containers in this model, from when they are coming off the vessel, moving through the container terminal yard, onto the train, to the hinterland, and then the reverse.
So one more question here from John. How has external disruption been modelled, e.g. power outage, strikes, etc.? Yeah, so we didn't consider those kinds of major disruptions in the modelling for this level of scope and the question it was trying to answer. All right, so I can't see any other questions. So I'll just say thank you very much for your time, and I hope everyone enjoyed that talk.
Thanks, Rhett. Thanks, everyone.
Okay, thank you.
Great, thanks very much, Rhett. Thanks very much, Jared, for the presentation and the great question and answer session.